Hello, Twitch. We're back from break. Yes, that seems to be working. We've got audio. Can everyone hear me and see the slides? Any problems? There's a new computer. Great. All right, so it's 4:56, so let's get started. So welcome everyone back from spring break. If you haven't seen already, your grades for your midterms should all be on Brightspace, so go and take a look if you haven't already. And we're going to be talking about Haskell today, but we're entering a sort of bridge part of the class where we're really only going to be talking about Haskell today. And for the rest of the class, we'll be moving into other programming languages and sort of studying language features that, were popularized or, are very essential to those languages and for which Haskell isn't a very good language to study. For example, we're not going to study object-oriented programming by looking at Haskell because Haskell has no object-oriented programming mechanisms to speak of. So we'll look at a more normal language in this case. And so this lecture, it's about lazy evaluation. And really, it's just because this lab that's going to be attached to this lecture, lazy.js, as its name suggests, is not about writing Haskell. In fact, it's about implementing Haskell-style lazy evaluation in JavaScript. And this will be a theme in a lot of the homeworks from now on, where we're going to have some language and we're going to want to implement the feature for that language so that we get some extra capabilities that we don't have ordinarily. So we'll do lazy evaluation. The lab is just a check on saying, one, do you know how to write JavaScript? And two, did you understand this lecture about lazy evaluation? So without further ado, let's get started. Okay, so there are 3 parts to this lecture. So first, I want to remind you all what lazy evaluation is. Now, we did talk about lazy evaluation way back when I told you about what it meant to write Haskell, but I want to remind you. And I'm also going to tell you about why laziness actually matters, because a lot of people don't really like lazy evaluation. And you might think, well, is it really that useful a language feature? Is Haskell successful in spite of lazy evaluation rather than because of it? I just want to tell you a little bit about, hey, this is actually useful stuff to know, and here are some really useful applications for it. Then we will dive into the technical content of this lecture. I'm going to tell you what graph evaluation is and how to do it. And when you're done with this, you'll be able to run Haskell programs in your head and understand when they are what is going to get evaluated when. So we're going to actually refine our execution model. So it's not just the realm of pure mathematics sort of things work out great. And it's not neither call by name evaluation, which we talked about in the lambda calculus, but rather we're going to talk about graph evaluation, which is an accurate way to talk about lazy evaluation, in particular because lazy evaluation only evaluates any given piece of work once. And we'll also use this as an opportunity to play around with stream combinators. So we did a lot of programming with lists in Haskell, but up until now, we've mostly treated them as just good old-fashioned arrays that you can use in normal programming languages. But here, what we're going to do is we're going to actually look at them not as regular old lists, but as streams. That is to say, possibly infinite sequences of data. And because Haskell is lazy, the list data type works for both regular lists and infinite streams cases, and you can do some nifty stuff with streams. And then finally, we'll just talk a little bit about some concepts external to Haskell itself. So one is we'll talk a little bit about how Haskell actually implements lazy evaluation. It's a pretty interesting topic in its own right. And we'll also talk about generators, a popular feature, perhaps most popular in Python, which has many similarities to lazy evaluation. Any questions before we get started? Okay, let's go. So, what is lazy evaluation? So let's just look at a program and see how lazy evaluation affects how we go about executing this program. So here's some Haskell code. What does it say? It says, well, define a function that takes two arguments, take the first argument, add 2 to it, and return it. So in fact, we're not going to use a second argument, y, at all. And now I'm going to call a function f with its first argument 5 and its second argument 25 to the 35,792 power. The exact computation doesn't matter, but one of these computations is cheap and one of these computations is very expensive, and we don't want to do the expensive computation. So in strict evaluation, in call by value languages, what we have to do when we want to evaluate this expression is we first have to evaluate the 5. Then we have to evaluate the second argument, the 29 to the blah, 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 blah argument, and only then can we actually evaluate the function f. And as you can see here, because we never actually use the value y, all of that evaluation that we did working on the second argument to this function is completely wasted. We didn't need it at all. So lazy evaluation says, hey, we're just going to not bother evaluating the arguments, and we're going to go straight to evaluating the function. And instead of passing in concrete values, because in a call by value language, you only ever pass in a number, an object, any sort of object that you'd expect in that case. With lazy evaluation, we will in fact send in so-called suspended computations, also known as thunks. So they're not a number, they're not an object, but instead they're these sort of like balls of code and data saying how to go about evaluating this expression at some later point in time. And of course, you don't see any of this, right? Because the moment you actually need the result, we will just go ahead and evaluate the thunk for you. You don't have to say anything explicitly. But that under the hood is what's happening in the language runtime. So, to summarize, in lazy evaluation, we don't evaluate expressions until they are needed. And we will make this precise today when we talk about the graph evaluation model. And furthermore, and unlike call by name evaluation, we will only ever evaluate an expression once. After we've evaluated it, we're going to memoize the result so that when someone else asks for that same result, maybe using the argument multiple times, we'll just give back the expression that we already evaluated. We're not going to bother trying to recompute it again. And so there's a little example here of call by name where, previously we just said, hey, if I have a big expression and then I substitute it into x plus x, I'll just, replace all occurrences of x with the right-hand side of a lambda. And of course, that will result in duplicate work if the expression in question is expensive. There's a little snippy side note here, which says, don't try this with side effects. And this is just a reminder, all the Haskell we've written, it's very confusing to understand when things actually get evaluated because it's lazy. So things get evaluated much later than you expect. And so if expressions could actually do, observable effects on the world, well, that wouldn't be very good. You'd have a very bad time understanding when anything actually happened. This is basically the IO lecture, right? We said, hey, we can't do this in Haskell, so we need something else, monads. Okay, so that is what lazy evaluation is, but I haven't told you why